So we are recording. Let's get started. Okay, so in Calc 1, you were exposed, or you should have been exposed to the fundamental theorem of calculus. Fundamental theorem of calculus. Sounds important, right? Well, it is, right? So this, many of you who have had me, we worked all semester at almost everything we did the whole semester was building up to the fundamental theorem of calculus. Okay, and so this is a bunch of symbols that mathematically represent the fundamental theorem. And in Calc 2, much of the course of Calc 2 is about integrals. Okay? And so in this equation here, all these symbols, where is it that we see integral? Where do we see integral in this statement? To the far left. Yes, you should recognize that the far left, or the left side of the equation, is an integral. Okay? And so because much of the course about Calc 2 is about integrals, we better know what this mathematical statement is all about. Okay? We better understand this backwards and forwards if we're gonna be talking about and looking at different applications of integrals. We need to know what the fundamental theorem is all about, because it's certainly incorporates integral to a great degree. Okay, so Calc 2, a big theme in Calc 2 is integration. As such, we really want to know the fundamental theorem really well. Okay, and not just as something to use to get an answer, but something that has lots of meanings, that it's tying together lots of meanings, and has an overall meaning, and then has lots of meanings within it as well. So we're going to spend the first day or two kind of building this up from scratch. So for those of you who had me before, hopefully this feels like review. Those who haven't, this will be a really important experience, okay? So we're making sense of this statement, the fundamental theorem of calculus, because integral is such an important part of it, and an important part of Calc 2. So to make sense of it, we're going to go through like 7 principles that are involved in the fundamental theorem. And so before we get to the 7, there's kind of this initial principle 0 that variables vary. Variables vary. And so when you see 2x minus 7 equals 0, what do you think when you see that? What do you think when you see that? What's that? He says x equals 7 over 2. Is that similar to what you thought when you saw that? X equals 3.5. Okay? Could x be 4 or 10 or negative 0.5?
Yes.
Some saying no, some saying yes. Could x be 4 or 10 or negative 0.5? He said it, some are saying no. He's saying it could be, but then the expression wouldn't be true. So think about what if x was this? What if someone with the same x is above, the same x that I've been talking about here, what if it was defined as the number of hours elapsed since your plane left the ground? Then, could x be 4? Could it be 10? Could it be negative 0.5? How could it be negative 0.5? So what would that be? Yeah, if you could say negative 0.5 would be half hour before your plane left, your plane took off. Okay, so when we define a variable as a changing quantity, that variable can take on many values. X can be 0, then 1.5, then 2. And so, sure, x could be, he kind of nailed it on the head there, x could be 4 or 10 and negative 0.5. It's just that those values don't make this statement true. Only when x is 3.5 is that statement true, but it doesn't mean that x doesn't vary through many values. And that's the way we want to think about variables, not as a fixed value, the unknown that we're solving for, but that it could take on many values. Okay? So in that situation, if I define x as the number of hours elapsed since your plane left the ground, then x takes on many values. In fact, it could be any real number. positive being number of hours after you took off, and then negative being number of hours before you took off. Okay, so then what about the variable dx? What would dx represent? So dx is also a variable, okay? So, and it's a variable that comes from the original variable x. What does the variable dx represent? Anybody? Yeah? A change in x, okay? Right, so dx, if dx was 3.5, let's call this negative. So what if dx was 2? And so can you be, yeah, so they both said a change in x. Can you be more specific? What exactly are we saying dx equals 2? And what do we mean by that? Does it mean 2 hours since the flight took off? The rate is doubling? What do you say? A change in x. So what does that mean?
From any 2 points, the change, or any 2 moments in time, the change in x is 2.
Right. So if x was 1, dx of 2 would be then later x is 3, right? So if x initial was 1 and x final, so we could say xi and xf was 3, that would result in a change of time of 2 hours. But it doesn't have to be, it could be any change in time of 2 hours. So it could be, maybe this is, we're flying across the Pacific here. So xi equals initial time is 10.5. If we have a change of 2 hours, then x final is 12.5. So x would be a particular number of hours since we left the ground. Dx is is a change that could start anytime, right? It's a change in time that could start anytime. It could start at 1 hour. It could start at 10.5 hours. But it's a change in time. Okay. So variables vary. We want to think of variables as taking on many values. Continuously, rather than a variable meaning just the answer to a question. It's one value, it's the answer to the question. I want to think about it as taking on many values continuously. Okay, so principle 1. Kind of the underlying main principle of all calculus, and then certainly the fundamental theorem of calculus, would be rate of change. Okay, rate of change. So here is an example. Suppose you're buying trail mix that costs $3.20 a pound. Okay, so after scooping some mix into your bag, you decide you want some more. What additional cost will you pay for 1.5 more pounds of trail mix? So now, first of all, before we talk, I want everyone to figure that out. So find an answer to that question. Before we do any discussion, everyone figure out what is the answer to that question. Everyone do it. You're writing or punching or something. Okay. Guadalupe, did you get it? What is it? $1.60. What do you think? Agree with that? You want to do it again? Okay. $4.80. And how did you get that? Okay. All right. And so it sounds like you've got a little device for doing what operation there? Is it 320? So it sounds like you explained the way in which you figured this out, right? The way that you're figuring out 320 times 1.5? Yeah. Okay. And that equals? Okay, so we'll just hold on to that for a second. Okay, so 320 per pound times 1.5 pounds is equal to 480. Okay, so now we want to put variables onto this situation. So we want to define variables with words, with phrases, with sentences, and decide whether the value is unknown or known in the given situation. Okay. So x, y, dx, dy, and m. Okay, so m is the, let me define some things here. M is the constant rate of change. And so I guess we have to define one of these. So what are we going to call x? Yeah, so the number of, so the, and yeah, the total number of pounds of trail mix. So we'll just give you that one. So the total number of pounds of mix in your bag. So now I want you to define what y would be, what the meaning of dx would be, dy, and I guess m we already did, but yeah. So define these other four variables in this situation, and then decide if it's known or unknown. So what about x? Is x known or unknown? Is x known or unknown? A couple of people want unknown. What do you think? In this situation, is x known or unknown? Is it 1.5? Yeah, so if you see it? So it says after scooping some mix into your bag, you decide you want more, and you're going to put 1.5 more pounds into your bag. So do you know how many total pounds in your bag? No. You don't know. Okay. So x is unknown. So work through and write out what y, dx, dy, and m is, and compare with those around you. Okay. Okay. Okay, where's Allison Coker? Allison, how'd you do on y? What do you think y is? Price per pound. Let's see. Is there something else in that list that should be price per pound? What would price per pound be instead of Y? Yeah, so that's the price per pound is that constant rate of change. Total cost? Yeah. So the cost of the X pounds of mix in dollars. Known or unknown? Unknown. Yeah, if we don't know the total number, if we don't know X, we can't know Y, right? Okay, what is the meaning of dx? Where is Jacob? Yeah.
That's the amount of pounds in the bag, like the change, how much you add or take away.
Okay, so it's a change in the number of pounds, how much you add or take away. Known or unknown in this situation?
It's
What it is? What? 1.5 pounds. So here in the situation I gave you, dx is 1.5 pounds. But it's variable, right? It's variable. It's not just 1.5. It could be 0.75. It could be, 3.1 pounds. Okay. In fact, so starting from 0, it could be any real number starting from 0, or -2. Okay. What about dy? Where is Alvaro?
It's change the cost of the X pounds of mix.
Okay, the change of the cost. Change in cost. Do we know that or not?
I don't think so. Because we only have one Y value.
Okay.
Because like it says after we like it's 320 per pound.
Okay.
But we don't know how much is in the bag, so we only have one Y value, so we don't know what the other Y value is.
Okay.
So it's unknown.
All right. What do we think about that? What he said. Adrian. So is dy known or unknown? He's arguing that it's not known because we don't know the starting cost. I think that's what you said.
Yeah.
Joseph, what do you think?
Yeah, it is known. It is the 480 because the change is $1. If the change is 1.5 pounds and if the cost is 320, then the change is $4.80.
So now he's saying it's 480. Is it 480? Okay. So the change in cost for a change of 1.5 pounds, the change is going to be 480. And M we talked about. M is the constant rate of change, so the number of dollars per pound. $3.20 per pound. Okay, so what I want to draw your attention to is this change in cost. How is it that we were able to find that change in cost? Well, you already did it, right? So when you did this calculation right here, you weren't thinking about all these calculus symbols, right? It was just common sense. It was like, okay, if it's 320 a pound and I'm going to put 1.5 more pounds in, then that's going to be $4.80 more. But calculus is symbol rich, right? There's symbols everywhere, so we have to know what symbols mean, and so we're practicing applying symbols to this. So what are the symbols? So how would we re-represent that easy calculation that you did at the beginning symbolically? Okay, so write an expression using these variables that computes that answer above. So what did we say? We said that the 480 was the 320 times 1.5. So now we want to rewrite that common sense calculation using symbols, right? Using symbols now instead of just common sense. So what would that be? Where's Ruth? dy
equal to
m times dx. What do you think? Okay, nailed it. Okay, so this statement right here is what we mean by constant rate of change. This is what defines constant rate of change. Said in words, it's that the change in one quantity is a constant multiple of the change of another quantity. So in this case, the change in cost is always a constant multiple of the change of the number of pounds of trail mix. And what is that constant multiple? It's 320. It's always, your change in cost is always $3.20 times as much as whatever change in pounds you have. Okay? So when you found $4.80 for the additional amount you would pay, in essence, you were doing this. You were doing dy equals m dx. Okay? If you're going 60 miles per hour on the highway and you travel for 2 more hours, how much more distance do you travel? You're going 60 miles per hour, you're going to travel for 2 more hours. How much more distance do you cover? 120. Common sense, right? Well, you just applied this, right? If you're going 60 miles per hour, constant rate, for 2 more additional hours, you're going to take 60 times 2 to get 120 total new change in miles covered, right? If gas is $2.50 a gallon and you put 10 more gallons of gas in your tank, what additional cost will you pay? $25. You just did this, right? Gas is $2.50 a gallon. You're going to put 10 more gallons in your tank. You're going to spend $25 more. Okay? Any question? Okay, so now you're going to remove 0.4 pounds from your bag, return it to the bin. When no one's looking, right? When no one's looking. Define each variable completely and precisely. Decide if its value is known or unknown. Yeah, so again, using phrases, write out the meanings of these variables. X and Y are the same as before. And then determine if it's known or unknown. Go, and then discuss. So, Lupe, Andre, William, Allison, who's back there, Jacob, who's here, Adrian's here, Joseph, Mitchell, Jacob Loeffler, Alvaro, there, Ruth up front, Haley is here, Hunter, Daphne, Philip, I see, Ariane, I see, and Hemming. Okay. Is it Hemming?
Yeah.
Hemming. What is dx? What does that mean?
Meaning of the
Yeah, meaning.
make it because we are removing
Okay.
the change of the mix factor is negative. So we know that it's negative 0.40.
Okay. Good. So it's a change in the number of pounds of mix, and we know that it's negative 0.4, right? If a decrease in a decrease in a variable means the change is negative, right? A decrease in the variable means the change is negative. Let's write this out. So dx. Sorry. Okay. So dx was equal to negative 0.4 pounds. All right. Ariana, how about dy? Okay. So how can we calculate it? It's going to be 3.2 times negative 0.4. Did you get an answer for that? And how can you have a negative number of dollars? Yeah.
It's how
Right, since it's a change in cost, you're going to pay that much less. So your change is going to be negative because you're going to pay that much less. M is the same as before. So again, we've got this relationship dy equals m dx, which is, it's a common sense thing you use all the time, but we have to recognize what it means and have these symbols in calculus for it. Okay, have these variable symbols in calculus for it. Okay, and so again, dy equals m dx. Negative 1.28 is going to equal to 3.2 times negative 0.4. Okay, new scenario. Soldier lowers an American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? And we want to define y as the height of the flag above the ground in meters. So I'm going to tell you that y is defined as the height of the flag in meters. Now we need to define the rest of the variables completely precisely, and then determine known or unknown. Go. So y we already know. Y is the height of the flag above the ground in meters. So you're going to define x, dx, dy, and m, and then say whether they're known or unknown. Talk it over once you're ready.
That's right, because if you multiply times the change in time, it's going up. It's negative.
Okay, Hunter, you're up. How'd it go?
Well,
How about x? What do you think x was?
X is the number of seconds the flag's been moving, I suppose.
Number of seconds that the flag's been moving. X. What do you think? Yeah, so I said the number of seconds since the flag left the top. So good, yeah. All right, y we already know. Height of the flag in meters. So what is dx? Change in the number of seconds, change in time since the flag left the top. So dy would be the change in height in meters. And m is the rate of change. And so m equals 0.75. Agree with that? Okay, right, because our height, positive height, is measured up from the ground, and what's happening to the height? Decreasing, so that m is going to be, hopefully you noticed or thought about that, that should be negative 0.75. Okay, so now we want to, oh, I never asked if they're known or unknown. So is x known or unknown? So the number of seconds since the flag left the top is unknown or known? Yeah, I told you the starting and ending times, right? So what I said was these are these values of x or dx? These are values of x, right? These are values of x. X is 0.6, and then a little bit later, x is 2.4 seconds. X is a variable. It varies. Starts at 0, and then if it's, we're just talking about since the flag was from the top, x starts at 0 and starts increasing. You can think of x as continuously increasing. And then if we pause time at, we could pause time at 0.6 seconds, and then pause time at 2.4 seconds. So, so if you can let x be the starting time, and it would be known, right? So what is dx? And where does that number 1.8 come from? Okay. Final time minus initial time gives the change in time. 0.8? 0.6. I was writing the answer down. So this is another important principle. Change in a quantity is the final value of the quantity minus the initial. So that dx is 1.8. And so how much does the height change from 0.6 seconds to 2.4 seconds? So I'm going to find the y value corresponding to 0.6 and the y value corresponding to 2.4, right? Do I need to do that? I don't need. I could do that, but that's a lot of work, right? Instead, I could use what? Rate of change. dy equals m times dx, right? So in 1.8 seconds, and a change of time of 1.8 seconds, the height is going to change negative 0.75 for every second, so I can just multiply. What do you get for that? Negative 1.35 meters. So it's not, is it below the ground? Is the flag below the ground? What is, oh wait, not necessarily or not at all? Yeah, it's not below the ground, so what's the negative mean? This is for the top of, it's, okay.
It's going to be the distance from 0.6 to, well, from 0.6 seconds from the top of the pole.
Okay.
So it's going to be change in height since 0.6 seconds.
Change in height from 0 seconds to 0.6 seconds?
No, 0.6 seconds to 2.4 seconds.
Right. So over that change of 1.8 seconds, the height changed by negative 1.35, or it moved down 1.35 meters. Okay, so this was just some practice to see that the change is the final value of the quantity minus the initial, and that's that. How do negative rates and play into this, right? So a negative rate will end up with, if you have a positive change in x, then a negative rate will give you a negative change in y. Okay, again, dy equals m dx. Okay, so let's look. Can you read these numbers on the side? Do they show up? So this is negative 0.5, and this is negative 1. This is 0.5. So I want you to talk about how does this graph that I'm showing you right here relate to what we just talked about. This graph, which is this blue line right here. This blue line is a graph that relates to what we just talked about, and so I want you to figure out how does it relate. Go. How does it relate to what we just talked about?
It's the rate of change graph because it's constant across all.
No matter what.
You've got like your formula, you're supposed to write out all the variables before you actually plug it in. Yep.
Okay, so what do we think? Who's up? Let's see. Mitchell. Where's Mitchell? Oh, you're up. So tell me about this. How does this graph, this blue line, represent or relate to what we just talked about with the flag?
So the blue line just represents the rate of change. So you see like it's a constant straight line
Okay.
at negative 0.75.
Okay.
So that rate's never changing, so that's why it's just a horizontal line.
Okay, so he's saying that this is the rate of change graph, the rate of change of height of the flag. Agree with that?
Yeah.
So what does that mean for the quantities that we're displaying on the axes of this graph? So I heard a few people say, oh, so the x is what and the y is what? And that's the right question to ask. So we can identify this constant rate, and that's important, but even better, we can also say what does the x coordinate represent, and what does the y coordinate represent in this graph? So let's take a shot at that.
So like at any time, any number of seconds.
Yeah.
So at any number of seconds, when you start pulling down the flag,
Right.
the constant rate is always -0.75.
Okay. And so then what is our x? What does x represent here? Number of seconds. It's the same x that we had, right? It's the same x that we defined before. Number of seconds since flag left the top. I'll say abbreviated number of seconds since the top, okay? And then what is our y coordinate? Is it Daphne? Yeah, so what does the y coordinate on this graph represent? The height of the flag. Agree with that? William's shaking his head. What do you think it is? Yeah, so the variable y that was the height, but now for this the y coordinate of this graph now is what we called m before, right? So m is the rate of change. So this is what we call a rate of change graph. So if I say, pick this point here, 0.4 and negative 0.75. So this point right here, what does that mean? That point, did I just add a point to this graph? Did I just add a point to this graph? What did I do? By drawing that dot.
Highlighting the point off.
I highlighted a point that was already there. How many points are you looking at? What you're looking there is an infinite number of points. As time increases, it's telling you what the rate of change is. So this particular point means what? That I highlighted means what? What does that particular point mean? Philip. Yeah. Yep. So tell me the meaning of that point right there. Okay, so it's both, right? So it's the coordination of the two values.
Yes, it's the relation, it's demonstrating the relation of that rate to
Okay, but that particular point means what? That particular point means
that at 0.4 seconds, the rate is changing at a rate of -0.75.
that's much better said. So you said no, it's good. No, I'm glad you kept going because originally you said that point is the rate of change.
Oh, I'm sorry. Yeah,
Well, no, it's okay. It's okay. No, and that's part of it, right? But that point is also saying at a particular time, this is the rate. Okay, good. All right. So, and this is just showing that exactly what we said. Now, at any given time, as time goes by, the rate is negative 0.75. All right. So, what might this graph be about? Think and talk about that one. What could this graph be about? So, talk.
Yeah, I know.
All right. What do we think? I think Joseph may have a handle on it. What do you think it's about?
That's actually what it would the rate of change would really look like as you're lowering the flag, because as you pull it, your rate of change is going to be at its maximum of 0.75, but then as you're switching hands, your rate of change is going to go to 0 because there's no change at that point. I used to lower the flag in the military, so I know that's how it works.
Perfect. All right. So does that make sense? All right. So exactly. So when you're actually when he's actually in the action of pulling, that's where the rate is maybe constant at negative 0.75. But in between, when changing hands, the flag is going to slow down and speed up, and then maybe for a moment pause. It'd be 0. The rate of change would be 0. Okay. So which is a more realistic rate graph? Which is more realistic rate of change graph? Okay. So, and what did we calculate? Before we calculated, how much does the height change from what time period? From 0.6 to 2.4? So we looked at this particular time frame, right? Okay, and this was our dx of, was how much? 1.8 seconds. And we got a corresponding dy of? We got that by doing m dx, right? M was negative 0.75, dx was 1.8, and we got our dy of negative 1.35. Okay, so what about the realistic version? Wait, did I have this in the wrong place? Is it 0.6 to 0.8? Okay, so this is where there's 0.6 to 0.8, 2.4. All right, so now 0.6 to 2.4. dx is what? Still 1.8. It's the same time change. All right, what's dy? Okay, so we no longer have a constant rate of change. So this is a much more difficult question, right? All of a sudden this becomes a lot harder because throughout that time period, the rate is changing continually, okay? So it's kind of how life is, right? You want something more realistic, you want something better, it's harder. You got to pay for it. You got to work harder, right? So you want something easy, quick and dirty solution, you know? Boom, we get it. Constant rate of change is very easy to work with and gives us fast results. But that kind of rate of change isn't always, a constant rate of change isn't always realistic. A changing rate of change is often more realistic. Okay? So, it's like, who knows? Can't use m dx. We can't use m times 1.8 because we don't have a constant rate the whole time. That rate is continually changing. So let's just talk a little bit. Is dy going to be more, let's see, is it going to be more or less negative than 1.35? So is it actually going to come down further or not as far in the real situation? Less far? She's saying less far. Agree with that? Because we still, a lot of the time we're negative 0.75, but the rest of the time the rate is, what, less negative, or slower, right? Slower going down. So we're expecting that if we were to get this value, the dy would be something less negative than 1.35. Would you agree with that? Maybe closer to -1 or something. That's just a guess. Okay, so how are we going to do this? How can we at least make some progress at finding what dy is since we don't have a constant rate of change? Yeah. Okay, and what benefit would that be?
We could then use constant rate of change to, like for every section that we break it up into,
Mm-hmm.
we could use constant rate of change for each interval and then just add all of those up.
Okay. Okay, good. So this is what we're going to do, what she said. So let's break it up. We're going to break it up into intervals of 0.3 seconds. So from 0.6 to 0.9, from 0.9 to 1.2, from 1.2 to 1.5, 1.5 to, oh, that's going to be too many. Let's see, 1.8. So it should be 6, 1, 2, 3. Okay, that's okay. 1.8, sorry. 2.1 and 2.4. Yeah. So I'm gonna slice up this change of 1.8 into 6 changes of 0.3. Okay, and then for each of those, I'm going to just estimate a constant rate that might represent the rate in that section. So what would I choose for my first interval here? From 0.6 to 0.9, negative 0.75. It looks like it's just pretty much negative 0.75 the whole way, right? So we'll call that M1. And we're going to be, M1 is going to be negative 0.75. Okay? And then I'm going to go in the second. So in the second, it does this. It's down here in the second interval, and then it comes up to 0, and then it's about 0. So we're just eyeballing. We need a constant rate that's trying to be like this changing rate in the second interval. What would we pick? It does, and there's no exact science to this. Make it easy on ourselves. What's that? She said negative 0.4. Yeah, I mean that's fine. Or negative 0.3 or negative 0.5 or put something in the middle. So if I took that constant rate right there, would it be somewhat reasonable, a constant rate to mimic this changing rate for that interval? You see that? So we're going to call it, that will be M2, and M2 will be negative 0.4. Okay? Third interval. Okay, but you notice in the third interval, I got a big chunk down here at negative 0.75. So to be different, what could we do? Yeah, maybe a little bit lower, negative 0.5, because there's more down here at negative 0.75. Okay, we're just estimating here. So this is M3. M4. negative 0.75 again would be M4. So my M3 is going to be negative 0.5. Okay, M5. So here we're spending a lot more time up, so I'm hearing negative 0.2. Sure. There's M5, and you guys wanted, running out of space here, so M5 is negative 0.2. Finally, M6, back at negative 0.75 again. You good? Agree? So what am I doing? When you have a changing rate, to get started, we can break up that interval, and we want to use constant rate of change because the math is really easy, right? So we're going to break it up into smaller sections, and we're going to try to come up with a pretend function that's built on constant rates, right? And hopefully get a good estimate from that. Okay, and so how are we going to get that good estimate? So now I've got a constant rate for this 0.3 seconds of negative 0.75, and then I got a constant rate for this 0.3 seconds of negative 0.4, etc. So how can I get my estimate for, so now this is an estimate now. What will the estimate for dy be for this entire interval of 1.8 seconds? Tell me how. Right. We're going to do negative 0.75 times its dx, 0.3, right? So that's what he called dy, like that, dy1, right? dy1 is the little change for that first interval from m1. Then what? That's how much change we get from our estimate of negative 0.4 in the second 0.3 seconds. Okay, go, finish it, find it, find your estimation, go. And what are we expecting? What kind of number are we expecting for the answer? Around what? Less negative than 1.3, so we're thinking maybe negative 1.1, negative 1, negative 0.9, something like that. Hunter's already got it. Did it agree with what we thought?
Pretty close.
Okay. What did you get? Someone else get that? Negative 0.78. What's the consensus? Those are too far apart. We need, that's not rounding error. Which one? 1.005. So at least we got, two people got that. Keep going. Don't stop if you've started. Let's get consensus. I should have been just typing this in up here instead of writing it.
I think the negative one is, I forgot the.
Someone else get this? Joseph and Ariana. We got anything yet? Did I miss one here? One more minus one. Yeah. I got negative 1.005 also. Okay. What's the units on that? Again, so when you get into calculations, don't forget to get yourself back into meanings of things once you're done with the calculations. So negative 1.05 means what? What is that? Meters, and it means? What does it mean? Okay, I'm hearing some good responses. In those 1.8 seconds, and that change of time, 1.8 seconds, the change in height was negative 1.005 meters. Was it exactly negative 1.005 meters? No, because we eyeballed it, right? We were eyeballing these constant rates to try to get something to work. Okay, so it's a first step towards it's a first step towards what we want, which is we want to know that number exactly. We want to know, given this changing rate at every moment, changing like this, what is dy? That's what we want. Okay, so this is a first step towards that. Okay, and so that's principle 2. Changing rate. So principle 1 was constant rate of change, understanding constant rate, dy equals mdx. Principle 2 is that most rates in the real world are changing rates of change, or changing rates of change. So that's what we just worked on. How much does the height change from 0.6 to 2.4 seconds since the flag is at the top of the pole? So we were able to do a little work and get an approximation for that. Okay, an approximation for that based on constant rates that are trying to be like the rate function, like a pretend rate function made of constant rates. Okay, so homework for tomorrow will be it'll be posted on Blackboard, and it will be written. If you don't have the book yet, that's okay because I provide the worksheet. So check on Blackboard for homework. It will be due at the beginning of class. Email me with questions here while we're waiting for office hours to get set. You can